Alright, at this point I have everything prepared to introduce a truly automated testing system called Qtest, based on software tracing. The idea of the system is really simple. Currently the target calls the code under test, COT, and sends the execution trace to the QSpy host application. The trace has all the information, but to use it for testing, you need to manually verify whether or not the trace matches your expectations. However, if QSpy could send a trace to yet another program on the host, such a program could verify the expectations automatically. I mean, all the information is on the host side already. This idea can be taken further. If such a program could also send commands back to the embedded target, it could tell the target to execute the COT in various ways, and then verify whether or not the produced trace matches the expectations. In other words, such a program could completely control the testing process. A testing system like that has several important implications. The testing strategy and verification of the test expectations are performed on the host computer, and they can be done in a different programming language than the embedded code. So it doesn't have to be C or C++, but it can be Python, for example. Compared to the traditional monolithic approach, where tests combine the testing strategy, execution of the COT, and verification of the test assertions, the separations of these concerns minimize the code running on the embedded target. This goes a long way in realizing the main principle of embedded TDD, which is avoiding the target hardware bottleneck as much as possible. And there are many other things that a decoupled testing system like that can do, while the traditional monolithic system cannot. I'll point out some of them when you see concrete examples. Very well then, let's do some testing. In the first Qtest demo, I simply continue with the LedBar example and the exact same code that was tested traditionally with the mock object. This will allow for a direct comparison of the methods and will also demonstrate that Qtest works for any code, such as Matt Chernowski's LedBar, that is not related in any way to the QP framework. So I'm still in the Unity LedBar directory and I'm using the same code under test from the src subdirectory. But this time the test code will be taken from the Qtest subdirectory. Here, the spy led.c test double is exactly the same as it was in the previous trace example. The test LedBar.c test fixture is very similar to the trace LedBar before, except instead of hard-coded calls to the COT, the real test fixture calls the qfrun function, which will wait for the commands from the test script. Also, the previously used trace function is now part of the qs-onCommand callback, which is called when the test script sends a command to the target. You can have a number of commands corresponding to the cmd ID parameter, so you would have more cases in the switch statement. For writing tests, you only need to remember that command 0 corresponds to calling LedBar set%, and param1 is passed to it as the percentage parameter. Okay, so now the really new element is the test LedBar.py Python script. For immediate comparison, I put the original Unity test with the mock side by side. Even if you know little about Python, the test script shouldn't be difficult to understand. But let me just first run the tests, and then with all the information on the screen, I'll explain the most interesting parts of the script. The first run will be on the host, because of course Qtest can run on the host as well, so I launch QSpy without any parameters. Next I change to the Qtest subdirectory and just type make, which builds the test fixture and immediately runs the Python test script. As you can see, this produces the familiar output in QSpy, and all tests pass on the Qtest side. Now let me explain the main elements of the Python test script and compare it with the original Unity mock test. You start each test with a test directive, where you provide a test name. The string you provide is no longer a function name, so it can contain spaces and be as descriptive as you like. Next, you send a command to the target, whereas the meaning of the command depends on what you've coded in your qs-onCommand callback function inside the test fixture. As you remember, command 00 means command 0 with param1 equal to 0. This will call the LedBar set% with the percent parameter equal to 0. In other words, this piece of the test script calls the COT. The expect directives that follow are the expectations for the generated output, one trace record at a time. As you can see, in the test script you call the COT first and then you verify the expectations. This is the natural order as opposed to the reversed order with the mocks. An interesting test was the one where the mock was programmed to deliver non-standard return values from the LEDON function. Controlling the return values from the test was the built-in capability of the mock, but it can also be done in the test script and the simpler spy test double. One way of controlling the return value from the test script is to poke some values in the target memory, and Qtest provides the poke directive for it. There are of course more directives like that, and they all form a small domain-specific language, DSL, for testing. The DSL is documented in the Qtest script reference manual, where you can read about all available commands. Of course, your test scripts can also use standard Python. But going back to the test run, I'd like to make some comments about the assertion test, which was a failed negative in the original mock test, but passes in Qtest, as it should. With Qtest, assertion failure produces a trace record like any other interesting occurrence in the target, so if you expect a specific assertion failure, the test will pass. But there is more to it downstream from the failed assertion. Please note that while most tests have the no reset attribute, the test immediately following the assert failure does not have no reset, which means that Qtest will perform the full reset of the target before running the test. Indeed, you see the target reset trace record immediately after the failing assertion. Before I explain why that is, let's change the test script by adding no reset to the test after the assertion and run it again. Now the test fails at line 35 with the message "No reset test needs reset." This is because Qtest noticed the assertion and its internal policy requires a full target reset before continuing testing. The rationale behind this policy is that the failing assertion means that something unrecoverable happened in the target, and in general you cannot trust the target software anymore. Therefore, execution of the following tests in that compromised state could produce wrong results, such as false positives. It turns out that the testing strategy that clearly separates the COT execution from verification can easily reset the target and continue with the tests, which is something that the traditional monolithic approach simply cannot do. All that traditional tests can do is the provision of the setup and teardown callback functions that are called by the test runner before and after each test in the group. Qtest supports the setup and teardown callbacks as well, but callbacks are simply not enough to truly guarantee that side effects of executing prior tests don't leak into the following tests. Callbacks cannot truly reinitialize the target, and I don't even mean the hardware, but simply the work performed by the low-level startup code, which includes clearing the BSS section, initializing the data section, calling static constructors in C++, etc. Yet, because traditional tests cannot cleanly reset the target between tests, many traditional tests pass only due to various side effects. Such false positive tests are the worst possible kind. They give you a false sense of security and allow the bugs to escape into production code. The capability to cleanly reset the target is a huge advantage, and therefore the default tests in Qtest are the full reset tests. Moreover, as you just saw, Qtest will notice situations when no reset tests are not to be trusted and will fail such tests. So let's restore the test script to the original form and run again. Here I'd like to point out yet another advantage of this approach over the traditional testing. Note that the tests run immediately without any need to recompile the code and download it to the target, which would be necessary with the traditional tests. This is what I mean when I say that this approach speeds up the TDD microcycle. Alright, so this was an example of testing interactions between the COT and one collaborating component, the LED in this case. But in the introduction you saw that a single event injected into an event-driven system might trigger interactions with multiple collaborating components. So now let's try to extend the LedBar example to interact with two collaborators, LED and SPI. Specifically, let's say that after turning an LED on, the LedBar2 also needs to send the power draw of that LED, returned from the LEDON function, to the SPI. Additionally, the SPI interface will have SPI begin transaction and SPI end transaction functions that need to be called before and after each group of the SPI transfers. I have prepared the Unity LedBar 2 directory with the code for this demo. You have here the new interface, spi.h, and you have the new CUT implementation in the file ledbar2.c, which I compare with the previous LedBar version. As you can see, the extended LedBar 2 uses both led.h and spi.h interfaces and adds the SPI calls per the specification. Now, in the traditional testing with mocks, you need to generate two such mock objects, mock LED and mock SPI. Subsequently, you use both mocks in the Unity tests. Please note that some of the Unity tests take liberties with the relative sequencing of the calls between the two mocks. For example, test LedBar 50% 2 on flawed completely separates the two sequences. You see all LED calls first and then separate SPI calls, instead of the interleaved sequence as specified by the sequence diagram. This test is flawed, so it should fail. Well, let's just check it. But before that, you still need to generate the test runner. Now you can finally build and run it. And the result is that all mock tests pass, except the false negative test for the assertion. But the run also contains false positives, because apparently the two mocks are completely unrelated. I'm sure that there could be some workarounds, perhaps to create one super mock that would combine the LED and SPI interfaces into one. But the need for this might be not immediately obvious to uninitiated, and there is definitely a potential of getting false positives. Alright, so now let's compare the traditional mock-based testing with the Qtest approach located in the Qtest subdirectory. The only new element here is the SPI test double. By now you should easily recognize that this code simply generates trace records from the calls to the SPI interface. The test fixture has only minimal changes to output the dictionaries for SPI and to replace LedBar with LedBar 2. Finally, the Python test script exactly matches the Unity tests, except that now all tests are reset tests, to be completely decoupled from each other. The Qtest directory contains a makefile for the host, but for the sake of demonstration, let's build and run the tests on the Nucleo L0 embedded target. For that, I launch QSpy to communicate with the target over the COM4 serial port, and I use make Nucleo file to make and run the tests. The results are now quite different than with the mocks. The assert test passes as expected, but the flawed tests that were passing before now fail as they should. There are no more false negatives and no more false positives, just the correct results. Also, the tests based on self-retracing easily fit in the small embedded target because the test fixture needs only to produce the traced output. In contrast, mocks have to remember the program sequences of calls, so they take quite a bit of the precious RAM. For example, the default memory size of CMOC is 32 kilobytes of RAM. Of course, this can be configured lower, but still it's several kilobytes. In comparison, the whole RAM footprint of the Qtest fixture is only 2.8 kilobytes, including the generously configured QSpy output buffer of 2 kilobytes and 128 bytes of the QSpy input buffer. As the final example, I'd like to show you the promised testing of a non-trivial hierarchical state machine. For that demonstration, I chose the QHSM TST example from Chapter 2 of my book, Practical UML State Charts in C and C++. The example is obviously a bit artificial in that it does not model any specific system, but it has been carefully designed to contain all possible transition topologies up to 4 levels of state nesting. I've used this state machine to test the internal implementation of the generic event processor inside the QP framework. I've also used it to explain the semantics of hierarchical state machines in my YouTube video, which you might want to watch. For today, it's only important to note that actions in this hierarchical state machine call the BSP display function to produce tracing information as to what exactly happened. For instance, entry action to state S2 calls BSP display S2 entry, while the exit action calls BSP display S2 exit. Similarly, action on transition H in state S11 calls BSP display S11H. So the SPY test double to trace the actions in this case is unusually simple and consists of instrumenting just the BSP display function. I chose to implement this right in the test fixture. The whole complexity of the testing is in the test scripts, because here I have actually two such Python scripts demonstrating the two alternative testing strategies. First is the functional test, where you are interested in verifying the actions performed by the state machine. This testing strategy is what I've been discussing all this time. This test starts with setting up the target right after the reset. Here the most interesting is setting up the global filter to all user records and suppressing all other records. This is important for testing because the expectations in your tests will obviously depend on what you choose to trace. The next important directive is setting the current state machine in the target to be the HSM object. This object will be then used in all subsequent tests. So for example, the first test uses the init directive to trigger the topmost initial transition in the current state machine object. The state machine initialization generates a trace of BSP display calls, which is verified by the expect directives. The next, quite large test uses the dispatch directive to dispatch various events to the current state machine and specifies the expectations. Again, as you can see, all these expectations are for the trace generated from the BSP display SPY test double. You can run just this functional test by specifying parameter test equals test QHSM funct.py to the make command. These functional tests generate quite a big output, but ultimately they all pass. But you have here also the structural test, which works completely differently. In this test, you are interested in verifying the structure of the state machine. Specifically, you are interested in the triggered transitions and the states exited and entered. For this, you don't actually use any SPY test doubles, so even this goes away. Instead, you rely completely on the tracing instrumentation already present in the event-driven framework. Because, as it turns out, almost all interesting interactions in the system funnel through the framework, so by instrumenting just this funnel, you can gain unprecedented visibility into the application, without adding any tracing to the application itself. In comparison, a traditional RTOS kernel knows only about tasks and inter-task communication mechanisms, all based on blocking, which have little use in event-driven systems. So here, your structured test simply activates the already present state machine instrumentation by setting the global filter to the state machine group. Please note that now the application-specific trace records are suppressed, so you won't see them in the trace. Now, an obvious question you might ask is, how would you write the expectations for trace records that you don't know, because you didn't put them in the code? Well, this is not how testing based on software tracing works, and has never worked. In practice, after you instrument your code, with printf or any other method, you first run the code, and only after that you scrutinize the produced output for correctness. So let's just do that. Let's comment out the expectations in the first test, as they didn't exist, and save the script. Next, let's open a terminal and start QSpy. Finally, in the second terminal, let's run just the structural test. This incomplete test fails, so this is your first intentionally failing test of the standard TDD cycle. But the test produces the output from the initialization of the state machine in this case. You can copy and paste this output into your test script and turn it into expectations. As you do this, you scrutinize the output, which is now much easier because it's rather obvious what the trace is saying. This part requires careful thinking to really make sure that the output is indeed correct. But with the existing output, this is actually easier than programming the mocks ahead of the run in the traditional method. You can of course repeat the run, copy, and scrutinize cycle for all other tests. This concludes this quick introduction to testing event-driven systems based on software tracing. The one message I'd like you to take home is that event-driven architecture, due to the inversion of control, is particularly suitable and beneficial for software tracing. Once you have the tracing, automating it for testing is just the next logical step. All these pieces fall into place and beautifully complement each other. If you would like to try the method, the code that I've demonstrated is part of the open source QPC framework available on GitHub.